Welcome to the Heavy Machines Solution Demo. Today we're going to look at how Planet Together APS can be used to solve many problems that heavy equipment manufacturers face. Advanced Planning and Scheduling, or APS, is a planning process by which raw materials and production capacity are optimally allocated to meet demand. Planet Together is an APS solution that simultaneously manages constraints for available materials, labor, machine capacity, and sequence-dependent setup. This results in optimized, feasible production plans and schedules, created in seconds or minutes for large models. Heavy equipment manufacturers, like most manufacturers, want to be able to produce what they need when they want it and in an optimal way. Their concerns may include bay scheduling, rework scheduling, and the use of subcontractors. At Planet Together, we have created a highly configurable modeling tool that allows us to simulate your production environment. We take all your real-time master data, current inventory levels, planned downtime, plus supply and demand signals to produce an optimal and actionable production schedule in minutes or seconds. In this video, we'll demonstrate how our tool can be used by heavy equipment manufacturers. In this walkthrough, we're going to take a look at scheduling a plant that manufactures heavy machinery. The plant can make the product in bays that have each piece of needed equipment. The plant can also inspect and rework any product coming in for refurbishing. The plant also has the option of outsourcing some of the work when capacity is needed. Planet Together will be used to model these three aspects of heavy machine production. The use cases we'll be walking through today include bay scheduling. This is where we have individual bays performing work on a single piece of heavy machinery being produced. The bay has all the necessary resources required to do the work, and the piece of machinery being produced will stay in the bay it was originally scheduled in until the work is complete. You can only work on one piece of equipment at a time in the bay. If you need to move the work to another bay, the entire route moves to the new bay. The next use case we'll look at will be subcontracting. This gives us the option of outsourcing some work when our plant doesn't have the capacity. The subcontracted work can reduce our profit, so our preference would be to schedule in-house when capacity permits. Subcontracted work will use different run rates as opposed to in-house production. When in-house, we know the rate per unit and schedule that exact amount of time. For subcontractors, we typically specify a duration regardless of the quantity produced. Some subcontractors may be faster than others. We'll see that we have options to schedule at any available and capable subcontractor. And the last use case we'll look at involves rework scheduling. This is a use case that can be used to model reusable space vehicles. A booster rocket is built, it then gets used in flight. The booster is then inspected and adjusted according to this particular booster's needs. We will model the original route and add QC steps. Once a QC step is performed, we'll know whether or not the associated production step needs to be repeated. If it doesn't need adjustment, we move on to the next QC step. In this first use case, we'll look at bay scheduling. This is where a single piece of heavy equipment is being worked on using multiple resources within a single bay. This allows the work to be completed without having to move the heavy equipment around the shop floor. In this model, we have two types of bays. One is configured to do iron work. The second is configured to work on hydraulic presses. We can see on the Gantt that we have two iron jobs and one hydraulic job, all scheduled on their appropriate bays. Here we can see that the first three bays can do the iron work. We can tell this by the green triangles showing other capable resources. We have a requirement that all steps in a single job need to be performed in a single bay. Let's see what happens when we move the first iron job from bay 1 to bay 3. We now see that the entire route for job 1 has moved to bay 3. We have an additional requirement that specifies only one job at a time can be scheduled in a bay. Let's see what happens when we try to violate this constraint by moving job 1 from bay 3 to bay 2 at a time when the kit process of bay 2 is available, but could overlap with an existing job. We see that the constraint is not violated, and the move job gets shifted to the right so that no two jobs are scheduled in a bay at any given time. This would be how we model bay scheduling. In this next use case, we'll be looking at scheduling work with a subcontractor. This may be needed when we don't have capacity available to produce the work on time. In order to keep our customer happy, we may choose to subcontract the work. Not all subcontractors may perform the same. We will have one subcontractor, modeled as resource sub-FMC, that can produce the work twice as fast as all the other subcontractors. All the others are pooled together, and we can select which one from the pool to use. When we decide to use a subcontractor, we need to add a QA step to the route to inspect their work before proceeding. You'll see this QA operations step added and removed automatically based on the route you choose. So let's review our model. Here we see two jobs with fairly simple routes. They both require an MFG-A resource for their first operation step. The second operation requires the MFG-B resource, where the final operation paints the product. The MFG-B resource has less capacity than the MFG-A resources. It has the potential to be a bottleneck. Because of this, we allow this operation step to be processed by a subcontractor when we don't have the capacity. I've placed some cleanout intervals on the Gantt to specify that MFG-B is down and not available for production until October 11th. This capacity constraint causes one of our jobs to schedule late. We can try manually moving the late job in front of the on-time job, but the work is still late. We see that we don't have the capacity in-house to get the work done on time, so let's subcontract the MFG-B step. One of our subcontractors, sub-FMC, is more expensive but does the work twice as fast. Our other subcontractors are equally interchangeable. They both have the same cost and take the same amount of time. Let's move the on-time job to one of the slower subcontractors using path B. This doesn't free up enough capacity on MFG-B to get the late job to schedule on time. Even if we switch between sub-other 1 and sub-other 2, we still have late work. If we move the late job to one of these slower, cheaper subcontractors, the work will still be produced late. Our next option is to use the quicker and costlier subcontractor, sub-FMC. It won't help to move the shorter on-time job, since the longer job will still be late based on its requirements for MFG-B and MFG-B's reduced capacity. So let's schedule the late job on the faster sub-FMC resource. Now that we've switched to path C using the sub-FMC contractor, we can see that all the work is now completed on time. We may have reduced our profit, but the customers will be happy. For our last use case, we'll be looking at how to model reworking or refurbishing a product. This happens with reusable launch vehicles. The boosters are originally produced using a very long route. We'll limit ours to 10 steps. Once the booster returns for being used, we need to inspect it and repair anything that needs repairing. We will use the original route with the addition of QC operations between each step. The QC operation determines whether or not the next step needs to be performed. We've created a route that includes all the original steps plus the QC steps. We've created this as a template in Plan It Together. We will use the Capable to Promise function, or CTP, to schedule a booster for rework. Let's start this process. First, we'll need to go to the Routing Templates board. Then we'll use the CTP from that board to generate the order. We can select the only template displayed, although there could be more. We specify that we want 1 unit by November 30th, and we will reserve the materials and capacity until the end of the year. We optimize the job onto the schedule and see the original 10 steps with QC operations between each. You might notice that the first 2 steps and associated QC operations can run in parallel. This is just to show you that not all steps need to be performed sequentially. We do require that the last operation not run in parallel, since it's the final QC step. As the job is run, someone from QC will make the inspection and determine as to whether or not the associated step needs to be performed. To do this, we will use the activity status on the Gantt board. Let's record that the first 3 steps pass QC, but the 4th does not. We use the Finish at Expected Values button after selecting the appropriate activities. Once we have finished the first 3 steps and their associated QC operation along with the 4th step's QC operation, we see the following. Now let's take advantage of the additional time freed up by completing the first 3 steps and associated QC operations. We can do this by either compressing the schedule or using the optimizer. I'll schedule using the optimizer. The job will now complete sooner than if the entire route needed to be rerun. This process will be repeated for the entire route of the booster being reworked. This concludes our quick heavy machine manufacturing demo. We were able to see the 3 use cases that included bay scheduling, subcontractor scheduling, and rework scheduling. Thank you for your time.